Next, to find the electric field due to the infinite plane sheet of charge. Suppose this is the plane sheet of the charge which has the charge distributed, say positive charge, uniformly over its surface, and this charge has the distribution with surface charge density sigma. Surface charge density sigma means it is the charge per unit area. To find the electric field at a point P, which is at a distance say y from the surface of the sheet, we choose a Gaussian surface, and this Gaussian surface is cylindrical. Gaussian surfaces are chosen in such a way that magnitude at the surfaces are equal and direction of electric field are either parallel or perpendicular to the surface area. Here, cylinder has three surfaces. One is the upper circular portion. It has the area say A1, and A1 has the magnitude A. Similarly, another surface area is circular, which is the bottom circle. It also has the area A, and we are representing this area by second surface, that is A2, and A2 has the area equal to A1. Third surface is cylindrical surface. We represent it by A3. It is also perpendicular to the surface and in outward direction. So there are the three surfaces in a cylinder. If we check the electric field, we are always perpendicular to the sheet by symmetry. So E is either perpendicular to the sheet in upward direction if we move up from the plane sheet, or it is perpendicular to the sheet in downward direction, because field due to the plane sheet will be in outward direction. Applying the Gauss law, for this case, we use integral, this is the flux, integral E dot ds, that is equal to Q enclosed by the Gaussian surface by epsilon naught. Here three surfaces, so we write the flux surface area 1, which is the upper circular area, and flux is E dot ds. Then surface area 2, which is also circular and it is the bottom circle, E dot ds. Plus third surface is the cylindrical surface, and we write here E dot ds, and it equal to the charge enclosed. This cylinder encloses a circle of area A, because bottom and top circular areas are equal to A in magnitude. Therefore, charge enclosed will be surface charge density, that is sigma, into area enclosed by the Gaussian surface, that is A, divided by epsilon naught. For first case, if we check, this direction is the E, here theta equal to 0 degree. In second case also it is 0 degree, but in third case, E and area A3 are always perpendicular, so it is 90 degree. Therefore, applying the formula, if we check, if theta is 90 degree, this flux will be 0, because cos 90 is 0. So remaining is integral for first surface E ds cos 0, plus for second surface it is also E ds cos 0 degree, plus third surface it is E ds cos 90. We have opened the dot product, and dot product A dot B is equal to AB cos theta. Here A and B are vectors, while this A and B are magnitude of the vectors, and theta is the angle between vector A and vector B. It is equal to sigma A by epsilon naught. So this implies that this cos 0 is 1, this cos 0 is 1, and this cos 90 is 0. So this integral will be 0. Remaining is integral 1 E ds plus integral 2. 1 and 2 refers the surface 1 and 2. That is the top and bottom circular areas. E ds equal to sigma A by epsilon naught. This implies that E is a constant by symmetry. We take it out, and the area of upper surface area plus E lower surface area, that is equal to sigma A by epsilon naught. This implies that E into, and upper surface area is A, so we write simply is A plus E into, again it is A, bottom surface area is also A, so it is equal to sigma A by epsilon naught. It is 2EA equal to sigma A by epsilon naught. A and A will get cancelled. this is equal to sigma by 2 epsilon naught. This is the electric field due to a plane sheet at a point P, and here we see that this electric field is constant in magnitude. It is independent of the distance of the point. E is independent of point location. That means due to the infinite charge sheet, electric field will be uniform above and below. It is independent of the distance of the point from the sheet. We have found that for a infinite charge sheet which has a surface charge density sigma, the electric field at any point P from the sheet has the electric field has value sigma by 2 epsilon naught. Now we take a case of the infinite charge conducting surface. Charge conducting surface. This charge conducting surface has some small thickness, suppose, and we know inside the conductor under static conditions, no charge can reside. All the charge lie on the outer surface. Therefore, we can say that if this is the infinite charge conducting sheet or surface, and we draw a cylindrical Gaussian surface over it, and this cylindrical surface cut an area which is a circular on the sheet. This sheet has the charge density sigma over its surface. Sigma is the surface charge density. This cylindrical Gaussian surface has three areas. A1, suppose it has the magnitude A and direction is outward direction. Similarly, another circular area is A2. It also has magnitude A and direction is outward left side. The cylinder cuts a circular portion of the plane sheet. Third of the area which cylinder has, it is A3, and it is cylindrical and it is perpendicular to the plane and in outward direction. So charge enclosed by this cylinder is sigma into A. This is the charge enclosed by cylinder. Now we use the Gauss law. Using the Gauss law, the flux is equal to charge enclosed by the Gaussian surface divided by epsilon naught. So applying this for all three areas, we find integral for surface 1, that is the circular surface, in E dot ds. Similarly for second surface E dot ds, it is also circular surface. Plus third surface is a cylindrical E dot ds, and it is equal to charge enclosed. Charge enclosed is the sigma A. Sigma is the charge density and A is the area enclosed by the cylindrical Gaussian surface and divided by epsilon naught. In case of first surface, this has the angle 0 between E and ds, area and electric field, it is 0 degree. For second surface also, which is circular portion, area and the electric field has the angle 0 degree, while the third surface, which is cylindrical, area is 90 degree. Therefore we open these dot products, we get for surface 1 it is E ds cos 0, plus for surface 2 E ds cos 0, and for surface 3 E ds cos 90 degree, and it is equal to sigma A by epsilon naught. Cos 0 is 1, and cos 90 is 0. So this is 0. This third integral will be 0. And if we check, the second surface is inside the conductor, and inside the conductor E is 0 because charge cannot lie inside the conductor. Therefore, only remaining portion is the integral of the first surface area, that is E ds. It is equal to sigma A by epsilon naught, and E is constant in magnitude being uniform at a distance. We can write it is integral for surface area 1 equal to sigma A by epsilon naught, and area of the first surface, which is circular, is A in magnitude. It is equal to sigma A by epsilon naught. And A and E will be cancelled. This implies that E equal to sigma by epsilon naught. Therefore, earlier we found for the infinite sheet which has thickness 0, E was sigma by 2 epsilon naught. But now we have used a conducting sheet surface which has some thickness, and inside the conductor field is 0. So field due to the conducting sheet or surface was E equal to sigma by epsilon naught. It is the twice of the earlier case, and it is distance dependent. It is a uniform in all over the space. We can visualize this case also as, and conductor has surfaces top and bottom surfaces. If this surface has a sigma charge density, say it is having a plus charge which is at the outer surface, and other surface of the conductor will also have the same charge density. And for a point P, if we take this surface 1 and this surface 2, the field due to the particular surface, for this surface with thickness 0, we can say field is in outward direction and it is E1, and it is equal to sigma by 2 epsilon naught if we consider the thickness is 0. Similarly, for other surface, the field will also sigma by 2 epsilon naught. That means for both surfaces, we say E equal to E1 plus E2, because these are in same direction. It is sigma by epsilon naught. So we get the sigma by epsilon naught for a thin charge conducting surface. Parallel plate capacitor. Parallel plate capacitor is a device of two parallel plates kept nearby. So these are the two sheets which are kept parallel to each other. One is given positive Q charge, another has suppose negative Q charge, and their charge densities are charged by area. So we can say it is sigma plus sigma is the surface charge density of the plate number 1, and minus sigma is the surface charge density of the plate number 2. This is the positive charge which is at the inner outside surface, and here is a negative charge which is at the outer surface of the second plate. To find the electric field at point P, if we check due to the positive plate, it is E plus, which is outward, and due to negative plate, it is E minus. Similarly, if we take a Q outside the plates, this is E plus due to the positive plate and E minus in opposite direction to the E plus due to the negative plate. Similarly, if we take another outside point R, which is left of the positive plate, so outward field due to the positive plate is E plus, and inward field due to the negative plate is E minus. If we check the E plus is sigma by 2 epsilon naught. It is the field due to the positive plate, and it is uniform, that is it is distance independent. Similarly, if we take negative plate, the field due to the negative plate is minus sigma by 2 epsilon naught. It is again the uniform field, and it is same at all points. Therefore, from the figure we can conclude that EP, that is the field at the point P, will be sigma by 2 epsilon naught in magnitude plus sigma by 2 epsilon naught in magnitude, that is equal to 2 sigma by 2 epsilon naught, and it is equal to sigma by epsilon naught. It is in terms of magnitude. Similarly, if we check the electric field at point Q, these electric fields are in opposite direction and equal in magnitude. So EQ will be 0. Similarly, ER will be 0.